In this video, we're going to cover section 1.4 on reaction mechanisms. The order of a reaction with respect to a given reactant is not determined by the stoichiometry of the reaction, because a balanced chemical reaction provides no information with respect to the mechanism of the chemical reaction. Now, a reaction mechanism is a proposed explanation for a chemical change. Experimental results may provide support for or rule out a proposed mechanism, but a mechanism may never be proven. So it's very important in science to recognize that we don't prove anything. We only provide experimental evidence to support or negate a hypothesis. So it's really important not to use that term when discussing scientific results and conclusions. Now, a reaction mechanism is defined as a collection of individual kinetic processes or elementary steps involved in the transformation of reactants into products. The rate law expression for a chemical reaction, including the order of the reaction, is entirely dependent on the reaction mechanism. In order for a reaction mechanism to be valid, the order of the reaction predicted by the mechanism must be in agreement with the experimentally determined rate law. All reaction mechanisms consist of a series of elementary reaction steps, or chemical processes that occur in a single step. The molecularity of a reaction step is the stoichiometric quantity of reactants involved in the reaction step. So we typically will categorize these elementary steps as either being unimolecular or bimolecular. There are some examples of termolecular reactions, but they're not as common. So when we discuss unimolecular reaction steps, these involve a single reactant species. So in this example of the dissociation of molecular iodine into two iodine atoms, we would refer to this as a unimolecular process or a unimolecular reaction step because there's only a single molecule on the left-hand side. On the other hand, a bimolecular reaction step involves the interaction of two reactants. And so in this example, we have nitric oxide reacting with ozone to give us nitrogen dioxide and molecular oxygen. Because two molecules are involved in this elementary reaction step, we would refer to this step as a bimolecular reaction step. The importance of elementary reaction steps is that the corresponding rate law expression for the reaction can be written based on the molecularity of the reaction. For example, for the unimolecular reaction, the rate law expression is that of a first-order reaction. So for the unimolecular decomposition of molecular iodine, the rate law expression for this elementary step is shown, where we have the rate constant K1 multiplied by the concentration of molecular iodine. Similarly, the rate law expression for the bimolecular reaction of nitric oxide and ozone is also shown. So again, for this elementary step, the consumption of nitric oxide is equivalent to the rate constant K1 and a product of the concentrations, both nitric oxide and ozone. And so you can see in this rate law expression, we have two terms, both to the power of 1, and so the overall order of this reaction is second order. And in the previous example, we would have a first order dependence because we have just a single reactant with an exponent 1. So when you compare the rate law expressions with their corresponding reactions, the order of the reaction is equal to the stoichiometric coefficient. For elementary reactions, the order of the reaction can be inferred from the molecularity of the reaction. However, this is only true for elementary reaction steps. You cannot infer molecularity for balanced reactions. only if what you're proposing or examining is certain to be an elementary step can you take the molecularity of that elementary step and propose a rate law expression like we did in these two examples. So keep that in mind when we're analyzing reaction mechanisms. We can propose rate law expressions for individual reaction steps if we know they are elementary reaction steps. So if you have any questions about reaction mechanisms or molecularity and how we use molecularity to devise these rate law expressions, by all means, send me an email. Thank you.